The first section in Chapter 6 is titled Solving Systems by Graphing. So first we have two vocabulary terms. Please write both of these down. We have a system of linear equations, and the word system just implies that we're talking about two or more linear equations. Remember, we spent all of Chapter 5 talking about linear equations. Remember that a linear equation is an equation of a line. A solution to a system of equations is an ordered pair that solves each equation in the system. And we'll talk about what that means to actually solve the equation. Also, each line in the system goes through the ordered pair that is the solution. So a solution to a system of equations is basically where the two lines intersect. First, we can determine if an ordered pair is a solution to the system by plugging that ordered pair into the equation and seeing if it solves, and we get a true statement. So I want to know for number 1 if 8, -1 is a solution to the system. Remember, in order to be a solution to the entire system, it must solve both equations. So what we're going to do is we're going to plug in 8 and -1 for x and y into both equations and see if we get a true statement. So for the first equation here, we have 8 minus -1, and we want to know if that equals 9. Now if we do same change, you'll see that 8 plus 1 is 9. We get 9 equals 9. So the equation, or the ordered pair, solves the first equation, which means the line does go through that ordered pair, but we need to make sure that the second line also goes through the ordered pair in order for it to be the solution. So we have 2 times 8, notice I'm plugging in the 8 for the x, plus 3 times -1, and I want to know if that's 13. So I get 16 plus a -3, or 16 minus 3, and that is 13. So we have 13 equals 13. So that means that the ordered pair solves both equations. It is a solution to the system. So to answer the question, yes, 8, -1 is a solution to the system. Let's look at another example. I want to know if 2, -7 is a solution to the system. So again, I'm going to take that ordered pair and I'm going to plug in the 2 for x, the -7 for y, and I'm going to plug it into both equations. So for the first equation, I have 2 minus -7. Again, same change. I get 2 plus 7, so I get 9 equals 9. That is true statement. Now we have the second equation, 2x plus 3y equals 13, and again I need to plug in the 2 for x and the -7 for y. So I get 2 times 2 plus 3 times the -7, and I want to know if that equals 13. 2 times 2 is 4. 3 times -7 is a -21, so I have 4 plus -21, which is the same as saying 4 minus 21. And I want to know if that's 13. Well, 4 minus 21 is a -17. That does not equal 13. So no, the ordered pair 2, -7 is not a solution to the system. It is a solution for the first equation, but not the system, or not both equations. So a solution to a system of equations can have one of 3 answers. If we have intersecting lines, there's going to be exactly one solution. If we have parallel lines, there will be no solutions, and hopefully that makes sense to you because parallel lines never intersect. Finally, if we have the same line, one line on top of the other line, then it intersects at every place, or we would have infinitely many solutions. Please make sure that you write this down, and we'll look at an example quickly of each one. So for the first graph here, we have intersecting lines. You can see that these two lines intersect at a point, and this would be the solution to the system. We could name that ordered pair. We won't do that here, but we could name that ordered pair as our solution. We also have parallel lines. They never intersect. So you can see why there is no solution here. Finally, we have the same line, and it's a little hard to see here, but the purple line and the green line are on top of one another, so we would say infinitely many solutions. because every ordered pair that's on the green line is also on the purple line, and I can make dots all over. So in order to graph a system and find the solution, we're going to graph both lines on the same coordinate axis, and then we're going to find their point of intersection. You may have to extend your slopes or extend your lines so that they cover across the entire graph so you can see where they intersect. And then we're going to write the point that is the solution in coordinate form x, y. So what I want you to do for number 3, there's your graph. I want you to find the solution to the system of equations. And again, we are going to find the solution by graphing both equations and seeing where they intersect. And I'll do this in 2 different colors. I'll do y equals 2x plus 1 in red. Remember, when we graph an equation, we need slope and an intercept, or we need 2 points, or we need a point and a slope. But we basically need 2 pieces of information. You'll see that these equations are written in slope-intercept form. So I'm going to start up at positive 1 because that's my y-intercept. My slope is positive 2 or 2 over 1, which means from my y-intercept I'm going up 2 and over 1, up 2 and over 1. And I mentioned in the previous set of directions that we need to extend in both directions. So I'm also going down 2 and left 1 because I'm not sure where these lines are going to intersect. So I want to make sure that my line goes all the way through the graph in case it were to intersect somewhere down here in the 3rd quadrant. For my next equation, I'll switch to blue. We have y equals 3x minus 1. So that one's going to be in blue. So we start down at negative 1. And again, we have positive slope. So I need to go up 3 and over 1. Positive direction, up 3 over 1, up 3 over 1, up 3 over 1. And I like to go in both directions, even though I already can see where the intersection point is. Kind of nice to have them both completely graphed. And then your answer to the solution or to the system needs to be written in an ordered pair. So you'll notice that this is the solution. That's where the 2 lines intersect. So if I name that point, it's 2, 5. So the answer is 2, 5. So really, if you think about it, there's not a whole lot new here because we know how to graph equations. We're just doing 2 of them on the same coordinate graph, and then we're finding where they intersect. So for number 4, again, I'm going to do these in 2 different colors. So I'll do the first line in red, and I'll do the second line in blue. So we have y equals negative 2x plus 4. The plus 4 is my y-intercept, so that's where I'm going to start. I have a negative 2x slope, so that's up 2 and left 1, or it's down 2 and right 1, whichever way you want to think about it, but it is negative slope. And I'm continuing to go down 2 over 1. Try to get straight here. For my next line, which I'll switch to blue, we have y equals 3x minus 1. So I'm starting down at negative 1. It's a positive 3, so I need to go up 3 over 1. And I can immediately see that my lines have intersected, but I am going to extend them all the way across the graph. Remember when graphing lines, oops, I didn't go down 3. Remember when graphing lines, I did ask that you have at least 5 ordered pairs. That still needs to be the case, even if you find where it intersects immediately. So again, this is my point of intersection. So I need to name that point for the solution, and it's 1, 2. Remember, you list the x coordinate first, then the y coordinate. Number 3 looks a little tricky because we have some fractions. Things are not in slope-intercept form. So it's your choice. Do you want to put things in slope-intercept form? Sometimes that's a little bit easier. I am going to do that. The first equation is a little bit tricky, so I'm going to switch back to red for the first equation, and I'm going to rewrite it down here. So I have x equals 3/4 y minus 6. I need to get the y by itself. So I'm going to add 6 to both sides. So I get x plus 6 equals 3/4 y. Now I need to get rid of that 3/4. You can do a couple of things here. You can get rid of the fraction first. Multiply everything by 4 would get rid of the fraction. So that would give me 4x plus 24 equals 3y. But now I have to get rid of the 3, so I have to divide everything by 3. So that's going to give me, I'm also going to rearrange it, y equals, oops, let's move it over here. Y equals 4/3 x plus 8. So now I can go ahead and graph that. I'm going to start up at positive 8, and I need to go up 4 and over 3. Notice I kind of run out of graph room, so I'm going to go down 4 and to the left 3. And I can't actually get 5 points on here because I run out of room, and that's okay. So there's the graph, y equals 4/3 x plus 8. On the next graph, I'm going to switch back to blue. All I need to do here is add the 3/4 x term to the other side. That's going to get the y by itself because those two terms cancel. So I get y equals 3/4 x plus 8. Now when I graph this, again, my y-intercept is up at positive 8. So hopefully you can tell that that's where the two lines are going to intersect immediately. Again, I can't go up 3 and over 4 because I run out of graph room. So I'm going to go down 3 and over 4, down 3, over 4. And I kind of run out of room again, but somewhere out here. Now when I draw this line, you can see that these two intersect at the y-intercept, which is positive 8. And we need to name that ordered pair. Remember, when you're naming an intercept, you're going to have a 0 in your coordinate. And in the y case, it's 0 for the x and 8 for the y. So that ordered pair is 0, 8. That's where the two lines intersect. Remember, that means that that ordered pair was a few more examples here. Number 6, we have x equals 1, and I'm going to graph that in red. Remember, when you have an x equals line, it's going to be a vertical line that goes through the x-axis at positive 1. So I have a vertical line that's going through the x-axis at positive 1. That's what an x equals line looks like, and that's something you're going to have to work to remember probably. Then if I graph the second line, my y-intercept is up at positive 4. And I'm going up 1 and over 2, up 1 over 2, up 1 over 2. And I want to go down 1 and over 2 in the other direction. And then I want to connect. This won't happen very often, but this is a case where we kind of end up in the middle a little bit. So if I circle this ordered pair, I know that the x value is positive 1 because that's the only place where that red line goes through. But I'm not actually at 4 or 5 on the y, I'm right in the middle. So it would be 1 and then 4.5 or 4.5, however you'd like to write it. You won't see this case very often where we have them intersecting at a fraction, but this is one where I think it is kind of easy to tell that it is a half. For our last example, I have 3x minus y equals 9 and y equals x. Now the first equation is in standard form and we do know how to graph using intercepts. However, you could run into the problem where if the line doesn't intersect at the intercepts and you didn't draw a real straight line, you might not have the correct answer. So I am going to go ahead and rewrite that first equation and put it in slope-intercept form. And I'm going to start by subtracting 3x from both sides. So when I do that at the bottom, I'm going to have negative y equals negative 3x plus 9. And I get rid of my negative 1 in front of the y by dividing everything by negative 1 or multiplying by negative 1. It does the same thing. But that gives me 3x and minus 9. So when I go to graph, I'm starting down here at negative 9 and I'm going up 3 and over 1 in the positive direction. This line has positive slope. So then I want to connect my dots, try to make it straight. Some of you like to use a ruler, that's fine. And then for the second equation, it's not intended to be tricky, but some of you may be a little bit tricked by it. Remember that I could also rewrite this as y equals x plus 0. So you can see that your y-intercept is at 0. If there's nothing back there, then it's a 0. And my slope is 1. In front of that x is just a 1. Remember, we don't have to write it, so it's up 1 over 1, up 1 over 1. And unfortunately, after I just said that we wouldn't have many that are fractions, it looks like this one is also maybe a fraction. So in that case, I'm really just going to say make your best estimate. I'm not sure that we'll ever see fractions again after this lesson today. And I'm trying to make sure that I graph that correctly. 1, 2. It looks like I did. So it's intersecting somewhere between the 4 and the 5 on the y-axis. Intersecting somewhere between the 4 and the 5 on the y-axis, or on the x-axis. So I would probably accept 4.5 and 4.5. Yeah, that looks good enough. So again, we won't see a lot of fractions like this, but just a couple of examples, maybe just to give you a heads up that it could happen. More often than not, though, they are going to intersect at an even or a whole numbered ordered pair. So again, remember, when you're graphing a solution, you're graphing a system of equations to find the solution, you're looking for where the two lines intersect. Remember that parallel lines will never intersect, so those will have the solution, you'll write no solution, and if it's the same line, you're graphing it on top of itself, then you have infinitely many solutions. You will work on worksheet 6.1 in class.